entire math major.
Those are the only two math classes that I have.
All right, I will begin with a word of prayer. Dearly Father, we thank you for this day again. I thank you for this class, and I just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So, let's see here. I have a few different things to share with you today. Let's suppose we've got a diagonalizable matrix. All right. What does that mean then? So that means that, there exists a basis beta such that what? Such that beta inverse A beta is equal to a diagonal matrix, right? And the eigenvalues are in the diagonal, right? But I just want to say a little bit more here. So if we say like phi beta of x is equal to y, let's just let like y be the eigencoordinates, right? So specifically in this context, we're talking about an n by n real matrix. To be clear, the formula is just beta inverse times x, right? In this special context of column vectors, this is the formula for the coordinate map, right? And so in this context, if we're studying the differential equation dx dt equals to ax, all right, where this is a n by n matrix, real matrix, all right? And again, I'm assuming it's diagonalizable just for the sake of discussion. Well, what would happen here if, I don't know, I could just take this equation and I guess I could solve, this says x is equal to what? Beta y, right? So I could say, well, this is ddt of beta y, all right, is equal to, ax, well, x was beta y, right? And beta is constant. So when you work out the calculus here, you can pull a constant matrix out of a matrix multiplication you're differentiating. Like it's a simple matter. If A and B are both functions of time, you can prove that there's a product rule for matrices, and it looks like this. This is going to be very, very surprising, but here it is. Here's the product rule for matrices. All right, there you go. Very unsurprising product rule. This is also true for like a product of a column vector times a matrix. So if the matrix is constant, then the derivative of the matrix is 0. All of that to say I can pull out the beta here, okay? And then I've got dy dt, right? Can you guys tell me what I would do next, maybe? Well then, if I multiply by beta inverse, I've got dy dt equals to what? Beta inverse a beta times y, right? But what is beta inverse a beta? It's the diagonal matrix, right? So this just becomes dy dt is equal to the diagonal matrix times y, right? Which specifically is, like lambda 1, y1, lambda 2, y2. Oh, my bad. I'll just write out lambda 1, lambda 2, lambda n times y1, y2, yn. All right, and what is the definition of dy dt, you guys think? It's what? It's dy1 dt, right? And so forth and so on, all the way down to dyn dt. So if you look at this, what do we have? We have got the equation dyj dt is equal to lambda j yj for all j. Can you solve those? If you're here, you've had calculus too, so the answer is yes, I can solve that. That's easy. That's separation of variables, right? Integrate. Lo and behold, we get yj is equal to cj e to the lambda j times t. And that's true for each eigenvalue. I mean, for each j, right? So that makes my total solution look like y equals to, c1 e to the lambda 1t, and so forth and so on down the line, cn e to the lambda nt. Now that's equal to what? Remember, that's equal to well, that beta inverse times x, right? So one more step, if you allow me this slightly circular argument, x is equal to, now if I let beta be, v1, v2, vn, isn't that funny? We didn't even have to reference the specific eigenvectors in this argument up to this point. This is the first time I'm actually writing down the vectors that are in beta. If we understand the theory, we have this ability. So x is beta y, right? But explicitly, when you multiply this times that matrix, what do you get? Well, you get c1 e to the lambda 1t v1 plus dot 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 plus cn e to the lambda nt vn. So in the case that your matrix is diagonalizable, the general solution to the differential equation dx dt equals to ax is simply obtained by taking constants times e to the eigenvalue times the eigenvector, and that's how you form the solution. I've derived it. With what? The diagonalization theory and calculus 2. Does that make sense? So you'd be like, okay, well, if my matrix is diagonalizable, then I can solve dx dt equals to ax with this, right? But what if it's not diagonalizable, right? Then how does this go, right? The obvious question. So let me give you a crash course here. So to solve dx dt equals to ax, and sometimes I use an r vector here, aka dr vector dt equals to ar vector, just to remind myself I'm working with vectors and not the scalar x, but you also can use x if you don't like the vector. It's all good. So how do you do that? Well, we need n linearly independent solutions. Let's say R1, Rn, then R equals to C1 R1 plus C2 R2 plus da 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 plus Cn Rn is the general solution. You can prove that such a general solution exists. I more or less did on Tuesday this week in the advanced analysis class. It's in like chapter 13 of the differential equations book. But it is picky analysis. But it can be proved that in fact the differential equation dx equals ax has a general solution set and it has to be of this form. Actually, the analysis proves it even when A is not a constant matrix. So even when A is a matrix of functions of time which are continuous on some interval, this is still true. All right? I know Soprano when I hear it. We're only going to solve in this course the case that A is a constant matrix. All right? And so just to, try to get to the point quickly because we don't have that much time on this topic. Linearly independent solutions, right? We want linearly independent solutions. If you put the solutions together into a matrix, that matrix should be what? Invertible, right. I'm glad that you did not say the forbidden linearly independent. That is very good. Invertible matrix. So we should expect the determinant of R1, R2, Rn is not equal to 0. This we need for linear independence of the solutions. All right? And also, check this out. If we have drj dt equals to arj for j equals to 1 to n, right? So suppose that we have n solutions, okay? Then notice that if we were to look at dr1 dt and then concatenate it all the way out to drn dt, this matrix of derivatives, then by assumption that matrix of derivatives would be AR1 for the first column, right? AR2 for the second column, and so forth until we finally get to ARN for the nth column. So let me just give us a name to think about this collectively. By definition, guys, if you have a matrix of functions, let's call this matrix here X. All right? The derivative of a matrix of functions is by definition the component-wise derivative of the matrix. So you just differentiate each component separately. Like the definition for dx dt means that this can be written as such. To differentiate a matrix, you simply differentiate component-wise. If you want, I can write the definition down. It's like, check it out. If you have A is a mapping from the reals to n by n matrices, then dA dt, the ijth component of that is equal to what?
The derivative of the ijth component of A.
Yeah. So you erase the parentheses. If you want me to make it feel like we're doing more, here, I'll make it look, here, it feels more definition-y if you do that, There, I feel like I really did something. But that is the definition. We differentiate component-wise. That's the definition you need to prove the product rule I wrote over there, which would make a good time pressure test question. Okay, I'm just kidding. I would have to assign homework on it to make that a reasonable question, or talk about it in class. Wait a minute, what did I just do? Let's see here. So let me stop. So dx dt is equal to this. It's equal to that. But remember the property we have in matrix multiplication, the column by column rule? This is equal to A times R1 all the way out through Rn, right? Which is A times X. So, definition, a matrix of functions for which dx dt is equal to A times X is called a solution matrix of the system dr dt equals to AR. All right? And what this calculation shows you right here is a simple theorem. This theorem simply shows you that the columns of a solution matrix are themselves solutions of the differential equation. Every column of a solution matrix is in fact a solution to the differential equation, because this calculation can be undone in the opposite way. Yeah. It's called a fundamental solution matrix if what? Fundamental solution matrix if the determinant of x is identically identically non-zero. Which is another way of just saying that the solution, the columns which form the matrix are linearly independent as a set of functions. All right. So it would be super nice if we could find a solution matrix to the differential equation dx dt equals to ax, right? Because if we could do that, then we'd have a set of n linearly independent solutions, and then we could form the general solution using those. That's it. So here's the deal. Definition. E to the TA is equal to the sum n equals 0 to infinity of TA to the n divided by n factorial. I'm sorry, my bad, guys. Let me erase the TA and put a b here. Let's put a b. We'll define e to the b. All right. So like if I put e to the TA, that is going to be equal to, e to the, my bad, it's going to be equal to the sum n equals 0 to infinity of like, t to the n over n factorial times a to the n, for example. This is the so-called matrix exponential. The matrix exponential. Let me write it out. So like e to the TA is equal to I plus TA plus 1/2 t squared a squared 1 over 3 factorial t cubed a cubed plus dot 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 dot, right? What are you putting in your calculator? I am very curious.
I'm trying to compare that to the. I'm trying to remember the definition of E.
Oh,
Limit.
it's the same. It's the same, but with x. So like, E is a number. I gotcha. Like e to the 1 plus 1 plus 1/2 plus 1 over 3 factorial plus 1 over 4 factorial. That thing, right?
And
Yeah.
I was just wanting to verify it.
Ah, okay, cool. It was blowing my mind that you had a calculator out right now. I was like, wait, what? Okay, anyway. So this is the matrix exponential. Now, you might wonder, wait. You're saying add together an infinite series of matrices? How's that a thing, right? How do you judge the convergence of an infinite series of matrices? And the answer is you take advanced calculus. So it's actually not that hard. You define a notion of distance on it, and then you define convergence of sequences in the same way you did in Calc 2, and then a series converges if the limited sequence of partial sums converges. You prove that the norm of that sequence is a Cauchy sequence, therefore converges, and then that gives you that the sequence of matrices is a Cauchy sequence, and thus therefore converges, because anyway, it converges for all A. Okay, just to get to the point, e to the b is defined for any b whatsoever. All right. So this is totally general. Any real matrix, this series converges. But it's more than that, because if we differentiate this, what do we get? What's the derivative of I? Very good. What's the derivative of TA with respect to t? A. What's the derivative of 1/2 t squared with respect to t. The differentiation with respect to a is a much more subtle question. That is genuinely an advanced calculus question. So derivative of t squared is 2t over 2, also known as t. But the a squared rides along. Derivative of t cubed, you got yourself a 3t squared over 3 factorial, also known as t squared over 2. A cubed, and so forth and so on. Tilt your head, squint, what you got here? Factor an a out. We've got a times I plus ta plus 1/2 t squared a squared, right? I hope you can see the pattern. We're looking at a e to the ta. What does this mean? This means the matrix exponential is a solution matrix. It's a solution matrix to dx dt equals to ax. So observation. E to the ta is solution matrix for dr dt, I should say dr dt equals to ar. Wow. They must have really done something. So what are the properties of the matrix exponential? Well, I'll tell you quickly. Here's a couple. One is that e to the e to the a times e to the b, man, is equal to e to the a plus b, provided ab is equal to ba. If a and b commute, the law of exponents hold. I can't help but tell you, and it's irrelevant to everything we're doing today, but I always tell you guys this. If they don't commute, you get this. And the plus and minus here, because I don't remember the sign. There is a plus and a minus, like it's for real. And what's past that is a infinite series of nested what are called commutators. The commutator of a and b is simply defined to be ab minus ba. So if the commutator is 0, all of this stuff, gone, and you're just left with this, all right? But if a and b commute, then we have, this is how the product of two matrix exponentials works, all right? So then what? So one of the things you can immediately get from that is if I have e to the a times e to the minus a, what do you get? A minus a, which is e to the 0. Now the reason, does a commute with itself? With minus, like a times minus a is equal to minus a times a, right? So it commutes. And e to the 0, search your heart, it's equal to?
Identity.
The identity. Well, that's, so there's a lot. So therefore, the determinant of e to the a, well, more to the point, e to the a inverse is what? E to the minus a, right? So the matrix exponential takes its values in invertible matrices. So in fact, not only is it a solution matrix, it is a fundamental solution matrix. All right? But there's more. I think in your homework, I had you guys prove something about this song and dance, if I remember right. I think I asked you guys to establish a very nice identity. I like this calculation I'm erasing. I showed it last semester in 221. It's written on Dr. Majerik's whiteboard because I think it's really neat. But anyway, it doesn't matter too much to this class, honestly. Where was I? Matrix exponential. Yes, what else can I tell you? Oh, yes. So here's an identity, another identity for the matrix. There are many. Here's one, like e to the a direct sum b. You can work it out. It is e to the a, my bad. It is e to the a direct sum e to the b. That's true. That happens. If I have e, here's a specific case of that. Like if you have e to the lambda 1, lambda k, let's say, like that. Think about what that is. That's the sum, n equals 0 to infinity, right, of lambda 1, lambda k to the power n. And there's 1 over n factorial here, right? But what is the nth power of a diagonal matrix? It's lambda 1 to the n, right? And I can bring the n factorial inside here. Fun fact, series of the matrix is the matrix of the series, provided that they converge, and these do, because what is the sum n equals 0 to infinity of these guys? This you know.
That'd be e to the lambda
Yeah.
1, e to the lambda 2.
Mm-hmm.
Just the direct sum of all of them.
Right, exactly, which, as you said, it would be indeed a very silly use, but nevertheless a legitimate use of the direct sum in the 1-by-1 case, right? That's true. This is really not what it's for, but let's get nuts, right? It's much more fun when they're blocks, yeah? All right. But here is the more interesting one. If I have P inverse e to the TA, let's say P, what's that equal to? Well, it turns out that that's equal to E, I'll factor the T out, P inverse AP. That's pretty nice, because we can make beta, well, we can make P the matrix of a Jordan basis. And I can even do more here. Like, what is e to a Jordan form, by the way? What is e to t times, let's say, the k by k Jordan form of lambda? How does that work out? Can we just calculate that? Yeah? How would you do it? Ah. Uh-huh. Cool. Oh, very good, very good. So we do lambda times ik plus, what was it? Nk, right? Fun fact. A scalar multiple. Oh, you guys remember the homework? Remember that homework early on? Find the set of all matrices which commute with all other matrices. What did we learn? Scalar multiples of the identity, right? So that we don't need all that for this, of course, but of course, lambda times the identity commutes with this nilpotent piece, doesn't it? And same for scalar multiples of it. So you see, I can rewrite this as, of course, e to the, t times lambda ik, right, times e to the tnk. But by the calculation we just did above, this is straight up e to the lambda t times the identity matrix, right? When these are all the same eigenvalue, you can just factor out e to the lambda times the identity. And what's e to the tnk. Well, let's write it out. I mean, it's the identity plus t times nk plus t squared over 2 times nk squared plus dot 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 plus t to the k minus 1 over k minus 1 factorial n to the power n sub k to the k minus 1. Past that, it's 0. That's a formula for the matrix exponential of the k by k Jordan block. We could write it out explicitly if you want. I don't want to do that, but you can express this in terms of, I want to do it. I'll do it for 3 by 3, okay? So this works out to e to the, man, lambda t. Now here I is, 1, 1, 1. None of this stuff has zeros below the diagonal. n3 squared is super diagonals. And so it just gives you a t here and a t here. n3 squared is the 0, 0, 1, 0, 0, 0, 0, 0, 0 matrix. And so you get the lone t squared over 2 up in here. That is the matrix exponential of the 3 by 3 Jordan block. And then you're like, but wait a minute, what if it's the real Jordan block? Oh, I'm glad you asked. Then we'd get a complex matrix, right? I mean, well, okay, so what happens if lambda is complex? Right, if lambda is complex, first of all, take your original differential equation, complexify it, you can find the solution matrix by looking at the Jordan blocks of the complexification, and then you can use the real and imaginary parts of that solution matrix to get a linearly independent column vectors, which are solutions to the original problem. I don't usually teach this material quite this way. I usually teach this in terms of the magic formula and generalized eigenvectors. Do you guys remember that from 221? It was at the very end. Some people don't remember it because they knew it wouldn't be on the ICE test, which is understandable because it wouldn't. And almost certainly this was not in your previous course, right?
It's been long enough ago.
Oh, okay, okay.
I wouldn't remember it.
Oh, okay, okay. But it's unlikely. So the other way to do this is what I call the magic formula, which is just a strategy for solving the differential equation by taking apart the matrix exponential piece by piece. See, every column in the matrix exponential is a solution to the differential equation, right? The name of the game is to find n solutions to the n by n problem. So if I can, there's two different paths to go down. The one I'm showing, kind of show you, this you can essentially patch together to directly calculate the matrix exponential if you're smart about it, right? The other way, though, is just to take it piece by piece, column by column, and basically strategically multiply the matrix exponential by the Jordan basis. And if you do that, you'll pick up generalized eigensolutions. Let me show you how. So the key to this scheme is what I call the magic formula. And I think I've done enough to derive it for you. Here's how it goes. E to the TA is equal to e to the t a minus lambda I plus lambda I. I added 0. But then this is equal to e to the, well, t lambda I times e to the t times a minus lambda I. Do you agree? I hope you agree. Because identity matrix commutes with the other one, right? And then simply, this is, again, e to the t lambda, scalar t lambda. Actually, I usually write lambda t there, right? Most people write lambda t. Whatever. And there's an identity matrix here, which I'm going to skip, because I'm going to expand this as the identity matrix plus t times a minus lambda I plus t squared over 2 and a minus lambda I squared, and so forth and so on, right? Eventually you have like t to the k over, or maybe k minus 1 factorial, k minus 1, a minus lambda I to the k minus 1, and so forth and so on, forever and ever, right? This is what I call the magic formula. What happens when you multiply the magic formula by an eigenvector? You could do this for any lambda. And if you complexify it, you could let lambda be complex just the same for a real matrix. It would still make sense. All right? So check this out. So if a minus lambda I times v is equal to 0, v1 is equal to 0, then what is e to the ta times v1 equal to? See what happens when v1 hits this? 0, 0, 0, only the I survives. So we get e to the lambda t times v1. That is technically a linear combination of the columns of the matrix exponential, but notice that a linear combination of solutions to a differential equation is again a solution to the homogeneous differential equation, because the differential equation has this linearity property, right? The sum of solutions is a solution. You can easily check that, right? If we're talking about solving dr dt equals to ar, can you see that? If I have dr1 dt equals to ar1, and if I have dr d2 equals to ar2, then the derivative of r1 plus r2 is a times r1 plus r2, which means it's a solution. That is exactly the thing we derived on the first board today. E to the eigenvalue times eigenvector. This is what I call an eigenvector solution. Now, in this context, if lambda is complex, what happens? If lambda is complex, right? If we have lambda is alpha plus I beta, and v1 is a1 plus ib1, then e to the alpha plus I beta times t times, a1 plus ib1 is actually equal e to the alpha t, factor that out, and it gives you a cosine beta t a1 minus sine beta t b1 plus I e to the alpha t sine beta t a1 plus cosine beta t b1. So in the case that you have a complex eigenvector, you get two real solutions, in fact, from the real part and the imaginary part, right? So this is the real part of e to the lambda t v1, and this is the imaginary part of e to the lambda t v1. And those will be linearly independent. You can prove it based on the linear independence that we already know from our previous work in part of the real and imaginary parts of the complex eigenvector. Remember, we proved those were linearly independent last class. So if you have a complex case, you get real solutions, but they end up having exponentials, cosines, and sines as such, right? What happens, though, if we have a generalized eigenvector of order 2? And it's in a chain, right? So like a minus lambda I v2 equals to v1, right? That would make a minus lambda I v2, a minus lambda I squared v2 equal to what? a big 0, right? And in that case, if we take e to the ta times v2, what do we get? We get e to the lambda t times what? Think about multiplying v2 through this. 0. Everything that's 0. I'll write down the two things that are non-zero. We get I times v2 plus t times a minus lambda I v2.
That's just V1.
Which is just v1. Very good. And there you go. That is the generalized eigenvector solution. I call that the generalized eigenvector solution. Again, if it was a complex eigenvector, you could split off the real and the imaginary parts, and you'd get two real solutions from that that would involve exponential of alpha, cosine beta, sine beta, and now a t. You get t times sines and cosines from a repeated complex root with a complex eigenvalue vector, a generalized eigenvector. What happens if we have a 3-chain? What if we have a minus lambda I v3 equals to v2? You see what's going to happen here? We get e to lambda t times what? Same thing as before, but now we get v3 plus t times, yeah, you probably know what the answer is. I'm just going to write it out. v3 t squared over 2 a minus lambda I squared v3, right? The next thing is 0, yeah? So that's what?
V3 plus t v2
Okay.
plus t squared over 2 v1.
Right, because when the first one gives you down to v2, and then the second application gives you down to v1. And there you go. Excuse me. Goodness gracious. Put it all together, we could solve any system of differential equations with constant coefficients, any system, using the matrix exponential and piecing together these Jordan solutions. Yep.
So this covers all linear differential equations.
Right, all linear homogeneous differential equations, as long as the A has constant coefficients. I mean, like the system we're solving, if I can go back to basics here for a second. I guess I'll do it up here. We're solving something of the form, you know, like dx1 dt. A civilized person would have written this at the start of class today. But, you know, I want to make sure I confuse the students, so I do this at the end. But this is the kind of system we're solving today. The point is that Aij is an element of the reals for all ij, okay? That's the context in which my solution holds as I've done it. Now, of course, you can ask the question, well, what if, what if it was not homogeneous, right? Like, how would you solve it in that case? And the answer there, I would have to give you is to go take advanced calculus. No, that's a lie. There, you're going to have to go to differential equations. That's where I teach that. I wouldn't put that on you here. I don't think I put that on you here. Who's done their homework already? Is it in there?
I
Don't remember. Don't remember it? I did assign you guys some differential equations from the textbook, but let's see here. Let's look at the notes for a minute. I have oodles of examples in the notes, and they're primarily done with the magic formula idea. I don't usually have the courage to teach directly from the Jordan form like we did today. Oh man, stop that. I got too many things open. I can't even read my, you know. You guys ready for the weekend? I'm ready. Let's see here. So this problem is kind of neat. This is actually what I started with today. So if you have this differential equation, you know, wow, man, where is it? Oh, it's based on the previous example, which is on the previous page, but so this differential equation right here, x prime equals to x plus y prime equals to 3x minus y, right? So the standard way this would be solved in 221 would be you find the eigenvalues, right? You find the eigenvectors, and you take a linear combination of the eigensolutions, and you're done, right? And that's fine. I think the only thing that is kind of a downside to it is like, well, what does this mean geometrically? Like, what's going on? Yeah, I mean, sure, we found the solution, but like, what's the significance of the eigenvectors to the solutions anyway, right? Like, there it is. It was easy enough to find the eigenvectors and the eigenvalue minus 2 and 1, and there's a solution, but what does this mean? Well, the next page actually shows you what it means in terms of changing to eigencoordinates. So like, if I change to eigencoordinates, the differential equation literally becomes dx bar dt equals to minus 2x bar. I would have used y1 and y2 at the start of this lecture. And dx dy bar dt equals to 2y bar. This is the differential equation recast in eigencoordinates. At this point, the system is uncoupled, right? The x bar just depends on x, the y bar just depends on y. You can separate and integrate both separately, and there's your solution. And of course, you can go back and derive the solution that we found by the eigenvector method. And I think that's kind of neat. And here's a picture of what's going on. These are actually pictures of the solutions. And you can see that there's something special happening along these two axes, right? Those are the eigenvector directions. All right? So, anyway. Let me go back a few pages. All right. Well, I wish I could remember what I put in your homework. I don't believe I put the non-homogeneous case in your homework. Did I, Daniel? No? Okay, good. Let's see here. So, you know, so like just some simple examples to end class with here, I guess. But if I have the 2x2 system, I find eigenvalues minus 3 and 1. That gives me eigenvectors correspondingly. And each one of the eigenvalues and eigenvectors, I can do either the eigenvalue times eigenvector, and that's the eigensolution, right? There's one of the solutions, and x2 is the other solution, and then which I get from the other eigenvector. And then you put them together, a linear combination of those gives you the general solution to the differential equation. That's in the case that the matrix is diagonalizable, we just do that, right? But sometimes it's not possible to find enough eigenvectors. I think that might be the case here. Let me just skip ahead here. Trying to find one that's got nastiness. Well, anyway, I've got every case under the sun in these examples here. So just because, okay, so this is something I wanted to talk to you guys about. Just because an eigenvalue is repeated, that doesn't mean it's not diagonalizable. Eigenvalues can be repeated and still have diagonalizability. All right. Now, if no eigenvalue is repeated, then yes, it does follow logically that it is diagonalizable because we have this theorem that eigenvectors for distinct eigenvalues are linearly independent. So if I've got n eigenvalues, I've got n eigenvectors, it's diagonalizable. Yay. However, here's an example. This one has the eigenvalue 7 three-peated, but obviously it's diagonalizable, right? Because it's diagonal. But it is true that in the context when you have, eigenvalues repeated, you may or may not have enough eigenvectors. Like this one, I think only gets 2 eigenvectors, as it turns out, which gives me these 2 eigensolutions to the differential equation. The third one's missing. Where is it? It's from a generalized eigenvector, which we get to later in the notes here. Let me skip ahead. Come on. There's the magic formula. Come on. There, we derived this stuff today. Here's the one where we were missing a solution, right? And off n class here. But that problem, we only had 2 eigensolutions. I go back and I look at another eigenvector with eigenvalue 2, I guess. Wait a minute. I've got too many examples. I'm returning to a different one. The point is we're missing a solution. And so we find a vector that satisfies the chain condition for eigenvalue 2. We get that. And then I plug it into the magic formula. And the magic formula pops out this third generalized eigenvector. I think I've shown you enough. I hope you can piece the things together. That's it for the material on test 2. Next week, we are going to inner products and norms, and chapter 6, that stuff will not be tested on, test 2. I was going to make test 2 next Wednesday, but then sports ball interfered.